Okay, so last application that we're going to talk about is using nanobots to make vaccines. So vaccines are important for obvious reasons, mainly protecting us from infectious diseases, so keeping us all healthy. The challenge with vaccines is they actually take a long time to develop. So vaccine development can take many, 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 many years. And also, vaccines have side effects, as we all know. So we think that the nanobots would be perfect for this application because we can make these synthetic components in a tube, and it can be done fairly quickly. So the question is, can we use these to make vaccines faster and safer? Some of the other advantages are that we know we can kind of engineer the nanobot to essentially resemble a microbe. We know that they can enhance the immune response, and I'll talk about that. And we know that they're safe and well tolerated in animals. And this is actually a pretty critical point, because if we're talking about ultimately making something that can go into humans, we need to understand the safety profile of that. And so we need to start in animals. So one of the first questions that we ask when we start these types of studies is what actually happens to these nanobots inside of an animal? Where do they go? And that's important to understand because for a variety of applications, you may want the nanobot to go to the spleen. You may want it to go somewhere else. So understanding how it's distributed in the body is very important. So the way we do this is we take nanobots and we fluorescently label them. We inject mice and we use a fluorescent imager to look for that fluorescent signal in the animal. So in this particular case, I'm going to show you data where we injected mice in the stomach, which is what we call intraperitoneal. Okay? And then 4 hours later, we ask the question, where do we see that fluorescent signal? And so in this particular case, what you're looking at here is the animal on the right in these images is the animal that received the fluorescently labeled nanobot. And the animal on the left is an animal that received just a salt solution, which is what we call a saline control. So you would not expect that animal to have any fluorescent signal. And what you can see is that that signal is localized in very specific places. So in the first image where the animal is laying on its stomach, you can see a very, very bright signal, kind of this yellowish, whitish signal where the bladder is. If we turn the animal on its side, you can see that same very bright white, orangish signal in the back, up a little bit higher, that's the kidney. And then if you flip the animal on its back, you can see both kidneys. So what this tells you is that when you inject this fluorescent nanobot intraperitoneal or into the stomach, a lot of it is going to be cleared through the kidneys. It's going to be cleared very rapidly, and ultimately the animal will pee it out, so you can see it in the urine. So if we take this image on the right, and we now say, let's take the organs out of this animal, and let's see what those organs look like. We can see, again, the kidney has the highest signal, which is what we would expect. It's what we saw in the whole animal. The liver also has a pretty high signal. We see some fluorescence in the spleen and very little in the lung. So what this means is, again, that if you inject these animals in the stomach with these fluorescent nanobots, most of that will be cleared out of the kidney and liver. Now, the question is, what happens if you actually give the animals this fluorescent nanobot a different way? So, for example, if you give it in the nose, does it go to the same places in the body? So many of you have probably had the flu mist vaccine, which is just a nasal mist up your nose. We kind of recapitulate this in mice. So mice naturally are nose breathers. They don't breathe out of their mouth. So if you just put some liquid on the nostril, they'll just breathe it in. So it simulates how you get the flu mist, essentially. So if we administer these fluorescent nanobots intranasally, as we call it, and we compare that with what we saw when we gave it intraperitoneal in the stomach, we see a very different distribution profile. So in this case, if we compare on the right side the intraperitoneal, which we saw already, with the intranasal, you can see that the signal in the kidney is pretty low. And that's very different from what we saw when we gave it in the stomach. It's low in the liver and it's low in the spleen, but it's very, very high in the lung. So what that tells us is the way that these nanoparticles, these nanobots, are distributed in the body is very much dependent on how you administer them. So it's different if you give the animal the fluorescent nanobot in the stomach versus the nose versus the muscle versus under the skin. That profile is going to look different. So that's something that we'd like to keep in mind when we're thinking about ways that we can use these. So one of the other things that's very important to understand is whether or not these nanobots are toxic okay? I'm not going to show you any of that data, but we've done a lot of studies to demonstrate that these particles, these nanobots, are not toxic to the mice. The mice tolerate them very well. So 2 important things. Where do they go in the body, and are they toxic or not? Okay, so how do we use these for vaccines? So the first thing that you need to do if you want to develop a vaccine is you need to have a target microorganism in mind. So what are you trying to protect against? If you're trying to protect against influenza, then you need to have, obviously, the virus, and you need to identify a protein from that virus. So in this case, you identify the microorganism, you isolate and express a protein, and then you have to do something else. You have to actually add what we call an immune-stimulating molecule. And the reason you have to do that is because proteins by themselves are not very immunostimulatory, okay? So adding that immune-stimulating molecule is really going to ramp up your body's immune response to that protein that you want the response directed against. So now you have your isolated protein, you have your immune-stimulating molecules. You can put these into the NLP to make your vaccine nanobot. Okay, so that nanobot has all of the constituents you need. It's got your protein, your immune-stimulating molecule, and now you're ready to vaccinate your mice. So we do that a variety of ways. We vaccinate our mice mainly intranasally, but we've done a lot of different routes in the stomach, in the muscle. So it just depends on what kind of a response you're trying to elicit. And then over time, you can sample this animal and you can start to ask questions about how the immune response looks to this vaccination. So how's the animal responding? So how do we do that? So again, after vaccination, we let some time pass, and we can actually take blood from these animals, okay? So we sample their blood various times after we vaccinate them. And what are we looking for when we do that? Well, when we take blood, we're actually looking for the presence of molecules called antibodies, okay? So this is one way that we can look at the immune response to our vaccination. Ultimately, the best test that we can do is to take this vaccinated animal, infect it with the microorganism that we're trying to protect against, and then ask the question, does that animal survive? Does it get sick? And so that's ultimately what these types of experiments look like, and is really what's needed to get these nanobots from, the bench top to people, to us, to actually use and be functional.
We funded them to solve an incredible technical challenge that no one else had been previously able to solve.